Welcome back to Discrete Mathematics. Today we're going to take a look at solving homogeneous recurrence relations. Now, last video we saw that we could solve geometric progressions like an is equal to 3, an minus 1. We defined the first one to be just a formula, an is equal to 7 times 3 to the n. And we want these equations to make computing specific numbers a lot easier. Now, with those simple relations, this is not a tough challenge. We saw two formulas for solving these geometric progressions. So we saw an is equal to d times an minus 1, where a0 is equal to k. We saw how to solve that one, and that was just an is equal to k times d to the n. So that's one way. Another way we saw was if we take an minus 1 is equal to k, with a0 is equal to some number c. We saw that an is equal to c plus the sum I equals 1 to n of k. So those are two different relations that we found solutions to, and these are very formulaic. You just plug them in and they're pretty much always going to be the same. What's a little bit more challenging, however, is when we get variations that aren't quite as simple as an minus 1, or an is equal to some number times a previous one. For instance, an minus 1 minus 6 an minus 2 is equal to 0. It's a little bit challenging, so we're going to introduce an interesting concept here, and I'm going to do this the very long way so we get each step. First of all, we want to transform this recurrence relation into an equation. So we need to get all of our an's to one side. Conveniently, this is already done. Now what we're going to do is we're going to multiply each term to the power x to the n. And we raise it to the n because, actually I should do this r to the n to be consistent with the other examples, r to the n. And this is consistent with the highest power here. So we have r to the n, and we subtract r to the n minus 1, and we subtract 6r to the n minus 2. Okay, and this is going to be equal to 0. So now we're going to divide by the lowest power of r here. So what we get is we're going to divide each term by r to the n minus 2 because it's the lowest one. So we're going to be left with r squared minus r minus 6 is equal to 0. This was a complicated way of saying that we take the smallest term and we just write it as a constant. We take the second smallest term, write it as a constant times r. We take the third smallest term and write it as the constant times r squared. You can kind of see a pattern of how we got from this step to this step. So if the second step confused you, don't worry about it. This is called the characteristic polynomial. So every recurrence relation has an equivalent characteristic polynomial. This is step number 1. So we want to get to this step. So as an example, what if we had an minus 3 plus 2 an minus 2 minus 6 an minus 1 plus 7 an? What's the corresponding characteristic polynomial? Well, this an minus 3 just becomes 1, because that's the coefficient. We have 1 an minus 3. We get 2 an minus 2. It's the second smallest number, so this becomes plus 2r. An minus 1 becomes minus 6r squared, and 7an becomes 7r cubed. So that is the corresponding characteristic polynomial. Okay. Now, the second step is to factor. So, r squared minus r minus 6, what does this factor into? Well, this can be r minus 3, r plus 2 is equal to 0. So our roots are going to be r is equal to 3 and r is equal to -2. So what this means is that for step 3, the form of our solution an is going to be some number alpha times 3 to the n plus some number beta times -2 to the n. The proof of why this works is a little bit long, but you can find it online in text form pretty easily. If I went over the form of why this works, this video would probably be at least 30 minutes if I were to explain it in depth. So this is more of a mechanics guide rather than a theoretical guide. So basically our roots are going to be raised to some power n, and we need some constants to modify that. So this is determining the form of an. Now we need to solve for some coefficients here. So what do we know? We know a0 is equal to 1 and a1 is equal to 8. So a0 is equal to 1, a1 is equal to 8. So we have our form, so we need to solve for our coefficients. So let's plug some things in. Okay, so 1, we have a0, so we take 0 for our n's here. So alpha times 3 to the 0 is equal, 1 is equal to alpha times 3 to the 0 plus beta times -2 to the 0, and 8 is equal to alpha times 3 to the 1, because we're dealing with a1, plus beta times -2 to the 1. So this is actually equal to alpha plus beta, and a1 is going to be 3 alpha minus 2 beta. Okay, so now we can just add the equations up and see what we get. So I'm going to write this a little bit more compact here. 1 is equal to alpha plus beta. 8 is equal to 3 alpha minus 2 beta. Okay, so we want to add the first equation twice. So we'll do this step by step. So we multiply the first equation by 2. So 2 is equal to 2 alpha plus 2 beta. We keep the second equation the same. 8 is equal to, it's a terrible 8. 8 is equal to 3 alpha minus 2 beta. And now we can add these up to solve for alpha. So 10 is going to be equal to 5 alpha, because 2 beta minus 2 beta, it cancels. So now we know that alpha is equal to 2. Okay, so using this equation, we have 1 is equal to 2 plus beta, so beta is equal to -1. Okay, now an, when we plug in our alpha and beta values, in fact, I'll just do this back up in the original part here. Alpha is equal to 2, and beta is equal to -1. So that is the solution to our homogeneous equation. So we can test it out. We can make sure it works. Okay, that's a little bit too far. How should I do this? Okay, well, we have some room over here, so we'll use this room. a0 is equal to 1. a1 is equal to 8. So how do we find a2? Okay, well, a2, we have to put some things on the other side. So more generally, we know that an is equal to an minus 1 plus 6an minus 2. So a2 is going to be 6a1, just a1 plus 6a0. So this is going to be 8 plus 6 times 1, which is 14. So a2 is 14. Let's see if our formula gets the same answer. a2 will be 2 times 3 squared plus -1 times -2 squared. So this is going to be 2 times 9 minus 4, which is 18 minus 4, which is equal to 14. So our formula gets the same result that our recurrence relation does. Again, this can be difficult. This is a long and challenging problem, so go through each step very, very carefully and go through solving for your coefficients carefully. That was one example, so of course we'll do another example. an minus 4an minus 1 plus 4an minus 2 is equal to 0. A0 is equal to 1. A1 is equal to 3. Let's get the characteristic polynomial. So an minus 4an minus 1 plus 4an minus 2 is going to have the characteristic polynomial r squared minus 4r plus 4 is equal to 0. Okay, so this is going to be r minus 2 times r minus 2 when we factor it. This is equal to 0. So our roots are 2 and 2. So this means that our formula an should be some number alpha times 2 to the n plus some number beta times 2 to the n. But then shouldn't alpha and beta be the same number? So we get a weird situation here. So normally, I'd say, yeah, this is okay, but what happens when we have similar roots is, say we have 2 to the n, then our second one is going to be n times 2 to the n. Suppose we had another root of 2, then our third one would be gamma n squared times 2 to the n. We'd have to multiply by n squared to have another root of root 2. Another root of 2. So when we do forms, if we ever have similar roots, then we simply just multiply by n however many times you have it in there. So we already have 2 to the n once, so we multiply 2 to the n times n. Okay, let's do what we did before. A0 is equal to 1, which when we plug in 0 in the n's here, we just get alpha. A1 is equal to 3, so this will be 2 alpha plus beta times 1 times 2 is 2 beta. So fortunately, we already know that alpha is equal to 1. So 3 is equal to 2 times 1 plus 2 beta. So 1 is equal to 2 beta. So 1/2 is equal to beta. So when we solve our recurrence relation here, we get an is equal to alpha, or not alpha, 2 to the n, because alpha is equal to 1, plus 1/2 n 2 to the n. So let's actually factor out a 2 to the n here. So this is 2 to the n plus, times 2 to the n times 1 plus 1/2 n. Okay, that would be our solution here. In fact, we could actually simplify this a little bit nicer. We could factor out 2 to the n minus 1. Actually, I should do one step first. 2 to the n plus n times 2 to the n minus 1, because we just divide 2 to the n by 2. And then we could pull out a 2 to the n minus 1, and this is just times 2 plus n. So that's another way we could do it. And that is the solution to the recurrence relation. And you can plug in some numbers yourself and see if you can solve them. So this is homogeneous recurrence relations. The most important part is the characteristic polynomial. So if you have roots that are different, then your an, so okay, let's say that r is equal to all the numbers, and you have all these different roots, and they go up to some number n. Then our solution is going to be of the form alpha 1 times 1 to the n plus alpha 2 times 2 to the n plus alpha 3 times 3 to the n, all the way up to some number alpha n times n to the n. I probably shouldn't have picked n for this, so I'm going to pick k. Goes all the way up to number k. Okay, that's a little bit nicer. Okay, so that's when the roots are different. This is going to be the form of your answer. Then you're going to have to solve a hell of a lot of equations to get your result. Now, when you have roots the same, so let's say r is equal to 1, 1, 1. No, let's not do 1. Let's do 3, 3, 3, and we do 3k times, and then we get a bunch of 2's, and we'll say this is 2, this is m times. Then our form an is going to be alpha 1 times 3 to the n plus alpha 2n times 3 to the n plus alpha 3n squared times 3 to the n. And this will add all the way up to alpha k n to the k times 3 to the n. So this is 3 to the n k times, so our final time we added up should be alpha k times n to the k times 3 to the n. And then we add up, of course, our 2's. So we have beta 1, 2 to the n, plus beta 2 times n, 2 to the n, and then we add all the way up to beta, so it's beta m times n to the m, 2 to the n. So a little bit of heavy notation, but I hope you get the concept that you have to multiply, the amount of roots you have by your numbers n here. So that way, let's say we have, for instance, let's have alpha 2 to the n plus beta 2 to the n. If we have this result, really it's the same thing as saying alpha plus beta 2 to the n. But we know this can't happen because if this did, then it would be geometric. But it's not geometric, so we clearly need something else in here to prevent it from being geometric. So this is why that doesn't work. Alright, so those were the two examples I'm going to do, and the last one is word problems. I'm not going to solve this, but I'm going to show you how to take a word problem and turn it into a recurrence relation. So let's find the recurrence relation for the number of binary strings with no consecutive ones. Okay, so let's be a little bit tricky here. We're going to take the nth number. So a to the n is the nth number. And this is going to be equal to all of the strings of length n that end in a 0 plus all of the strings of length n that end in a 1. So if we have a bunch of numbers and this is the nth digit, then it can be either a 0 or a 1. So we're going to separate the two. If the digit ends in a 0, then we can have any number prior. So the rest can be written in an minus 1 ways. However, if the last digit is a 1, then we can write the rest in an minus 1 ways, but the n minus 1, so let's say this is 1, because we can't have any consecutive 1s, this number right here has to be a 0. So it can only be the fact that an minus 1 has to end with a 0. Okay, which means that an minus 1 plus, well, if an minus 1 ends with a 0, then the rest of the sequence an minus 2 can be anything they want. So an minus 1 plus an minus 2, and this is the recurrence relation. Of course, we need to know that how many ways can we have 0, or a string of length 0? 1. How many ways can we have a string of length 1? It can be either 0 or 1, so it would be 2. And this is your recurrence relation. So the number of binary strings with no consecutive ones can be found with this recurrence relation. And again, to sort of go over the example and why I did it a certain way, suppose we have a binary string of length n. This is some n. It can either end with 0 or 1. So we say that an is equal to an that ends in 0 plus an that ends in 1. The number in brackets above it are ends with. So the number of ways that the recurrence relation can end is with 0 or 1. So if it is a 0, then all of these ways can be written however they want. So that's going to be an minus 1, because there's an minus 1 ways to order the rest. If, however, n ends with a 1, then this n minus 1 has to be a 0. So then the rest can be ordered in an minus 2 ways. So there's 2 cases we have to deal with. So that's just the thought process of how we go through this thing. So in the end, we get an is equal to an minus 1 plus an minus 2. Where does this seem familiar? Where does this seem familiar? I swear we've seen this before. In fact, we have. This is Fibonacci. So what's this doing here? It's kind of weird. Just being up in binary strings. Well, they're actually related. Fibonacci is a very, very common sequence seen in a lot of relations that you wouldn't expect. So it's probably best if we solve for it, right? If we know what Fibonacci looks like as a formula. And I could solve the whole thing on camera, but I'm bound to make a mistake. And I'm bound to make a mistake because the algebra is very difficult, and talking while writing and doing math is not the simplest thing to do. So instead, I'm going to give you a skeleton of what's going on. So an is equal to an minus 1 plus an minus 2. Our first 2 numbers are 0 and 1. So what we do is we have to find the characteristic polynomial. So we get an minus an minus 1 minus an minus 2 is equal to 0. So we get r squared minus r minus 1 is equal to 0. Using the quadratic formula, we get that r is equal to 1 plus root 5 over 2 and 1 minus root 5 over 2. So then we get this form, alpha times 1 plus root 5 over 2 to the n plus beta times 1 minus root 5 over 2 to the n. And then when we solve for our coefficients a0 and a1, we end up getting that an is equal to 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. All this is algebra. This technique follows the exact same method that we did for the previous question, and as your homework, I challenge you to do the algebra and get this result to prove that you can do it. If you have any questions on how to do this, leave it in the comments below and I will answer them, because if you can do this, if you can solve this with the skeleton and understand why each step works, you understand homogeneous recurrence relations and how to solve them. So that is your goal. Do this, and if you can't get this, leave them in the comments below and I will explain step by step how to do this, but I want to avoid this for now. There is also some more practice questions on the midterm at trevtutor.com in the Discrete Math 2 section. You should be looking at midterm number 2 for that information. So that was homogeneous recurrence relations. Next time we'll talk about non-homogeneous recurrence relations, which you need to understand this to do non-homogeneous recurrence relations. It is crucial that you can do this because you need to have this process on autopilot, because this process is only a part of homogeneous recurrence relations. So, once you get this, move on to the next video. If not, ask questions, I will answer. See you guys next time.